Hello, and welcome back. We've been talking about momentum for a little while now, and momentum is a way for us to describe motion, just like our kinematics and dynamics, we describe velocity and acceleration. Momentum is another way to describe and quantify motion. We talked about how that quantity of momentum changes with impulses that occur from external forces. And if we define a system to be closed, that is to say the mass doesn't change and there are no net external forces acting on it, well, if we define a closed system, then we have this law of conservation of momentum that says that for our system, momentum will not change in value at any point in time. But that does beg the question, well, what are these cleverly defined systems? And the focus of today's video will be on trying to identify these types of collisions. There's three that we have today. Because these collisions, these three types of collisions, are all ones in which momentum is conserved. We want to also be able to correctly label collision in a problem by the type of collision that it is, right? We want to be able to correctly identify this is this type of collision, or this other scenario is a different type of collision. We want to be able to identify them. And then our third part is identify the conserved quantities. Now this is important. Our conserved quantities are always going to be momentum in these cases, but there may be other conserved quantities that are useful to take into account. So those are our three main goals today. We're going to start off by, first I'm going to list out the type of collisions that exist. The type of collisions that we're going to look at are elastic collisions. We are going to look at inelastic collisions. And the third type of collision we're going to look at are called explosions. And first, what do these look like? Can we get a visualization of this? And we'll start with elastic. For an elastic collision, we could imagine two objects. I'm going to draw these two carts, and they're going to head towards each other. So this is our initial. I'll put an I there for initial. So they're going to go towards each other, and then after they collide, because they are on a collision course, after they collide, what is going to happen is that the carts are going to bounce off of each other and possibly go in opposite directions. It doesn't necessarily have to go in opposite directions, but we'll assume here that they do go in opposite directions. So this would be an example of an elastic collision. Elastic collisions are defined by the fact that they bounce off of each other, that they do not stick together. That's very important. They do not stick together. We can identify carts by saying this is cart 1, cart 2, and when we look at this, we identify our system. Remember, identifying systems are very important, and here your system would be identified as both carts, meaning that if you were to calculate the momentum of the system, momentum initial of the system will be the momentum initial of cart 1 and the momentum of initial of cart 2 added together. Of course, they're vector quantities, and that's important because cart 2 has a negative momentum here because it's moving to the left, and we typically define that as leftwards. So our elastic collision, they bounce off of each other. What about for inelastic collisions? Well, inelastic collisions are of the type that when we have two objects heading towards each other, we'll start again with these two carts, and they are heading towards each other. Cart 1, cart 2. This is our initial case. Well, after the collision, what's going to happen is our two carts are going to be stuck together. So after the collision, cart 1, cart 2, they're going to be stuck together, and they're going to be moving maybe in one direction or to the left, or maybe they're not moving at all. So our two carts stick together after the collision. That is an inelastic collision. They stick together. And you can relate this to your usual definition of elastic, right? Elastic, think bounce. They bounce off. Inelastic, they stick together. And then that raises the question of the third type of collision. The third type of collision is one in which you have an object. Let's say, for example, this is going to be a tough drawing, but let's say we have a projectile we launch into there. Maybe it's a firework, right? The firework launches as a projectile into the air, And after the firework explodes, what's going to happen? Well, fragments are going to scatter all over the place. We have different fragments of our object after it explodes. It's literally an explosion. It's what you think of when you think of the word explosion. And here's the interesting thing. When you talk about your system, you define your system to be your object that is your projectile. Here it's your firework, right? And what's important is after the explosion occurs, you consider your system to be all of the individual pieces. All of the individual pieces which are going to spread out. So that's your initial and your final for your explosion. Now when we take a look at this, we start to ask the question, well, what is unique for each of these type of collisions, right? And we'll start off again with the elastic collision. And here's the interesting thing. With our elastic collision, there is actually excuse me. For our elastic collision, there's actually going to be a second conserved quantity. And that's that the initial energy is equal to the final energy. This can be proven, and I'll probably do so in a later video, but for right now, we will maintain this as true. And what does this mean? Well, that means that for our objects, we can sum together for our elastic collision. We might have two or more objects, right? So we would sum together the initial energy of object 1 and object 2, and that must equal the final energy of object 1 plus the final energy of object 2. Now it gets even a little bit more useful, because when we think about the collision takes place over a very small space and time. If you remember when we were talking about potential energy dealt only with space, right? It dealt with like the potential energy of gravity, how high above the ground are you? Well, you're not changing significantly in altitude as you go throughout a collision. So what other collisions occur? Well, maybe there's a collision that involves a spring, but even then the time period is so short the spring is not going to compress or decompress much if it's involved in a collision. So more to the point, we can say there is no potential energy going on here, or no change in potential energy, I should say. There's no change in potential energy. What else? Well, we define these to be closed systems. If we define these to be closed systems, that means the net external force is 0, which means that the total work done on the system is going to be 0 as well. So this really only leaves one type of energy to be involved here, and that's kinetic energy. So we could rewrite this not just as general energy, but very specifically, nope, not final, that the initial kinetic energies of both objects added together must equal the final kinetic energy of both objects added together. And keep in mind that all of these values, they're going to be positive. They're going to be positive values, which means that for each of these, oh, I put a plus there. I should have put an equal. My apologies. That means for each of these values that they're going to be greater than 0. If they were equal to 0, then nothing is going to be moving and the objects aren't going to collide. So they must be greater than 0. So that is your kinetic energy. And we would call this conservation of kinetic energy for elastic objects only, right? For elastic objects, we have conservation of kinetic energy. Along with that, we have the conservation of momentum. That says your initial momentum of one cart plus your initial momentum of your other cart must equal your final momentum of your two carts. And I know I'm using the word cart here, but this applies to anything. This applies to anything, not just carts. This applies to any objects that are going some sort of a bouncing off type collision. So this would be elastic collisions. And very specifically, this would be considered perfectly elastic collisions. Oftentimes we do see a drop in energy from collisions. This drop in energy is because you hear sound from a collision. That sound is of a form of an energy. Oftentimes objects will heat up after they bounce off of each other. That heating up is a form of lost energy. So this is really just an approximation of an elastic collision, one which we would call a perfectly elastic collision. But this is a good approximation nevertheless. This is a good approximation that can handle a great deal of problems. Again, this is for two objects that are bouncing off. However, when we talk about an inelastic collision, for an inelastic collision, we do still have that your initial momentums are going to equal your final momentums. You still have conservation of momentum. That is absolutely going to be true, and that should be final. P final 1. And I know I flipped the order. It doesn't matter which order you add things in, though. So we have this idea now of conservation of momentum. Still holds true. But then you think about the energy. And again, here there's not going to be any significant potential energies. Work is a little bit different, though. And not because there's external work. There is still the case that no external work is done, but internally, when we look at an inelastic collision, there's always going to be some deformation. There will always be some deformation that needs to occur for a collision to be inelastic, for your inelastic objects to stick together. And since there is some deformation happening, that means that there's some sort of internal transfers of energy, and these internal transfers of energy takes away from the net kinetic energy. So what we can say here is that our initial kinetic energy is actually going to be greater than your final kinetic energy. So you do have some loss in kinetic energy here. You have some energy being lost due to deformation. There are other places energy is lost to as well, creating the sound of the collision, the heating up that's inevitably going to occur during a collision. But it is the case that your initial kinetic energy and your final kinetic energy are going to be different. So you don't necessarily have conservation of energy here. But you do still have conservation momentum, and that's going to be useful. It's going to be useful because when we look at our scenario here, right? Let's go back to saying we have two carts. Our two carts are going to be initially heading towards each other before the collision, and then after the collision occurs, we'll have our two carts, and we'll say these two carts are going to be stuck together, moving to the right. And when we take a look at this, we will grab our conservation of momentum, and we will say, well, the initial momentum of cart 1 is going to be mass 1 times initial velocity 1, vector arrow over top. And then we're going to add to that the mass of cart 2 times the initial velocity of cart 2. That is our total initial momentum right there. And we're going to set that equal to mass of cart 1 times the final velocity of cart 1, not cart 2. And then we're going to add that to the mass of cart 2 times the final velocity of cart 2. And then we take a look at this and we understand that our cart 1 and our cart 2, well, they're going to be stuck together. They're physically connected. They are mechanically connected. And since they're mechanically connected, they will share the same final velocity. So what I can do instead of writing out m1 v final 1, m2 v final 2, I could instead write out m1 v final plus m2 v final. Because again, they have the same final velocity. Or better yet, I can write out the sum of m1 and m2 times v final. And that gives us our conservation of momentum equation for inelastic collisions. And then we're left with one final type of collision. And here's what we're going to do. We're going to look at two carts again. This time our two carts are going to be initially stuck together. They're initially stuck together, but we're going to put some sort of an explosive powder in between them. And that explosive powder will stick them together. And they're going to be moving in some direction. When we take a look at this, these carts are going to be initially moving in some direction. After a little while, we're going to trigger the explosion. And when we trigger the explosion, it's going to send the left cart to the left, and it's going to send the right cart to the right. And we'll name these cart 1, cart 2. And we get this explosion, sending them in opposite directions with some final velocity of cart 1, final velocity of cart 2, whatever those might be. Now when we take a look at this again, we define our system to be both carts together, both before and after the collision. And when we do this, we can be certain that our initial momentum is going to equal our final momentum for our entire system. However, our kinetic energy is going to be different. Because here we initially start with some energy being stored in this explosive material. Whatever that material is, there's chemical energy stored in there. And that chemical energy is released into the system, sending the carts on their way. We're transferring that chemical energy into kinetic energy. And because we do that, we would say that our initial kinetic energy is going to be less than our final kinetic energy. And it's not because we're creating energy here. It's just transferring from a different type kinetic energy. From a different type chemical energy. So we're really left, again here, just like with our inelastic collisions, we are left here with a conservation of momentum equation. And when we do this, we can look at our initial momentum, where we have mass 1 times velocity 1 initial. But here's the thing, both of our carts are mechanically connected at first. So they have the same initial velocity. So we can really write m1v initial plus m2v2 m2v initial. And we can set that equal to our final momentum, which is going to be m1v1 final. And here we do have different final velocities. m2v2 final. And we can combine the left-hand side here to be the summation. m1 plus m2 times v final. Not v final, v initial. And that gives you your equation for your explosion. So we go back to our initial questions. Did we meet our goals? And we ask the question, identify the different types of collisions. There's 3 of them. There's elastic, inelastic, and explosions. In each of these cases, we are defining our systems to have 0 external net force. We are defining our system to have no change in mass, and that's important in the explosions, why we identify all of the objects after the explosions being part of our system. So we don't have a change in mass, and we don't have an external net force. And when that occurs and we have our different types of collisions, you have elastic, inelastic, and explosions. How do you identify them? Well, in the case of elastic collisions, the objects bounce off of each other. They're never connected to each other. In the case of inelastic collisions, we have our objects starting apart, colliding with each other, and sticking together after the collision. And with explosions, you have your objects initially connected together, but some sort of a release of energy sends them flying apart. So they start together and then they separate. And that's how you identify the different, what type of collision is occurring. And then once you have that collision that occurs, the conserved quantities, well, for each of these, momentum will be conserved, meaning your final momentum and your initial momentum have the same value. But special for elastic collisions, we have that kinetic energy is also conserved. That kinetic energy initially is equal to kinetic energy final. So those are your conserved quantities. All right, in the next video, I'm going to go over a brief couple of sample problems, show you what the processes of solving these different problems are. But I think that's good for this video. If you have any questions, be sure to ask, and I will see you next time.